So I'll start. So in this video, we're going to start subgroups, right? Subgroups. So far we have seen the very first class they will give one set, and we have to verify there is a group or not. And second, we will move on to permutation groups or symmetry groups. And then we have seen order of an element, and then we have solved many theorems based on order of an element and group. And we are moved on to isomorphisms on groups, right? So I finished this topic. So we are going to start subgroups. After finishing subgroups, we will be moving on to cosets and Lagrange's theorem. So subgroups I will take as live classes, and cosets and Lagrange's theorem I will send the recorded videos for cosets and Lagrange's theorem. And then we will see cyclic groups, normal subgroups, quotient groups, homomorphism subgroups. That's it. The group theory will be over. So today subgroup I will try to complete. Cosets and Lagrange's theorem will be sent as recorded video maybe tomorrow, and I will complete, after that I will complete cyclic groups, normal subgroups, quotient groups and homomorphism subgroups, right? Yes. So after that we will move on to ring theory. So first we are going to start subgroups today. So suppose actually it's a very simple process, So let us say G is a group, right? So if I say G is a group, G is closed, G is associative, G has identity and G has inverse. Now I am going to make a subset. I am going to take a subset H of G, and this subset will be a subgroup if H itself a group. If H itself a group. That is, we are taking a subset H of G, and if this H itself a group, that is H is closed, H is associative, H has identity and H has inverse, then we say this H is a subgroup of G, right? So this subset, H is a subset, and this subset will be a subgroup if H itself is a group, right? So in book they are giving a different name to subset, which is called complex. So they are giving a different meaning for subset, right? Don't worry about the term complex X, right? So it is nothing a fancy word for subset. You know what's meant by subset, right? So a collection of some elements from the set, and so therefore the complex X will be a subgroup if this set itself a group, right? So complexes and complexes and subset both are same. So any non-empty subset H of a group G is called complex of the group G, right? So any subset is called the complex of the group G. So let us define complex. So definition: complex of a group, complex of group G. Any non-empty subset, any non-empty subset H of a group G is called complex, right? So of all the subsets, you just take the non-empty subset, so that any non-empty subset of G is called the complex of a group G, right? So any non-empty subset of a group G is called a complex of a group G. Now we will define definition of subgroup. So I am defining subgroup in terms of complex, right? So we know complex is a non-empty subset. So this non-empty subset H will be a subgroup if H itself a group. A non-empty subset H is a subgroup of G if H itself a group. A non-empty subset H is a subgroup if H itself a group, right? Or we can also define in terms of complex. So a complex if a complex is a group, then it is a subgroup, right? So we will not use definition. So a non-empty subset H is a subgroup if H itself a group, right? So this is a basic definition for subgroup. You are taking a subset and you calling that subset to be a subgroup if that subset is itself a group, right? Yes. So these are the definition of subgroups. Now we will see some examples. So some example 1. So I am going to give 6 examples. So example 1. And whenever you are saying a subgroup, remember, for example, if I take Z4 addition modulo 4, so it has 0, 1, 2, 3. You cannot simply take 1, 2, 3 and you cannot call this as a subgroup. It can be a subset, 1, 2, 3 can be a subset, but in order to be a subgroup, this set has to be a group. This set has to be a group, but surely there is no ID element in this set, right? What is ID element? Z4. So 0 is not in this set. So surely this will not be a subgroup. It will be a subset, but it will not be a subgroup. So if it is a subgroup subset, it does not imply that it is a subgroup. But if it is a subgroup, it will be a subset, right? So that is what they are telling, that complex does not imply subgroup, but subgroup imply complex. Complex means subset. Complex form of group means a subset of a group. So now we will see some examples. So example 1. So G is equal to 1 minus 1 minus I minus I. 1 minus 1 I minus I. This is the fourth order of unity. So H is equal to 1 minus, this is a subgroup. This is a subgroup. You can see 1 is in G, and if you take any 2 elements, you just take it is also closed, right? It is also closed because you just take 2, it has only 2 elements, so just take 2 elements. So 1 into minus 1, so 1 into minus 1 is minus 1, so minus 1 is also in H, so therefore it is closed. And for associative, you just take A to be equal to what, B to be equal to what, C to be equal to minus 1. It is not that A, B, C are distinct. So I am taking A to be 1, B to be 1, C to be minus 1. So you just verify A star B star C is same as A star B star C. Here the operation is multiplication modulo 4, sorry, normal multiplication, right? Normal multiplication operation. So A star, so what is B star C? B star C is minus 1, A is 1, and A star B is 1 into 1 is 1 into minus 1. Therefore this is equal to minus 1. So this set is closed and as well as it has associative. So clearly 1 belongs to H. So therefore this set has identity element. And what is the inverse of 1 and inverse of minus 1? So inverse of 1 is 1 again, because 1 into something will have to give you 1, so therefore this 1, so therefore this belongs to H. And inverse of minus 1 is minus 1, so therefore minus 1 also is in H. So therefore this 2 elements itself a group, so therefore this H will be a subgroup of G. So second example, example 2. Example 2, the additive group of even integers is a subgroup of additive group of integers. So G is equal to Z comma plus. So I am taking S to be equal to 2Z. 2Z. So therefore this will be a subgroup 0 plus or minus 2 plus or minus 4 plus or minus 6. This will be a subgroup, right? So you can see this set itself a group. ID exists and it is closed, it is associative, you can easily verify. And inverse also exists. Inverse of 2 is minus 2, inverse of 4 is minus 4, and inverse of 6 is minus 6. ID is 0. What about odd integers? What about odd integers? That is, what about odd integers? Plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 6. Is this a subgroup with respect to, I have taken G to be Z, I have taken the subgroup S to be 2Z, so we have proved that it is a subgroup. What about 2n plus 1Z? It is not a subgroup because 0 does not belong to H, that is there is no ID element in the subgroup. So we can easily say that the set of all odd integers is not a subgroup of integers with respect to addition. Now example 3, the multiplicative group of positive rational numbers is subgroup of multiplicative group of all non-zero rational numbers. So example 3, G is equal to Q star, right, non-zero rational number except 0 with respect to multiplication, because if you include 0 then inverse of 0 is undefined, so therefore we will exclude 0 in a rational number and the operation is multiplication. So therefore I am taking H to be equal to a set of all positive rational numbers with respect to multiplication. The multiplicative group of positive rational numbers subgroup of multiplicative group of all non-zero rational numbers. This is a subgroup. Again you can verify that. Fourth, this is subgroup, right? So this set contains positive rational numbers, so 0 and p by q, and this p comma q, p positive rational numbers, so this has to be positive. So p and q belongs to, we will say this n, it is n. So therefore the elements will be the real line after the real line excluding irrational number. So if you take any element, suppose if you take 1 by 2, inverse will be 2, right? So therefore this is a subgroup. It has id element 0, and for every element there is an inverse, and clearly it is closed and associative. The fourth, the additive group of integers, subgroup of additive group of all rational numbers. So G is equal to Q comma plus and H is equal to Z comma plus. Then H is a subgroup. So this is a group set of all rational numbers under addition. You already know. And I am taking H to be equal to Z comma plus, set of all integers with respect to plus. Again H is a subgroup. So H is a subgroup means H itself a group. Then example 5, the alternating group AN of all even permutations of degree n is a subgroup of symmetric group Pn. So example 5, so G is equal to Sn, then H is equal to An is a subgroup. An itself will form a group, right? For example, if you take S3, so the elements are I, 1, 2, 3, 1, 3, 2. I am fixing 1 and changing 2, 3, fixing 2 and changing 3, and fixing a 3 I am changing 1 and 2. So these are 6 elements. Now what is A3? A3 set of all even permutations. So even permutation means a cycle of length, if the number of transposition is even, it is called even permutation. So you can represent every cycle as a disjoint transposition. So I can write 1 2 3 as 1 2 1 3, and this as 1 3 1 2, and it is already in transposition. Your cycle of length 2 is transposition. So A3 I is always even permutation. So we already discussed. So A3 is I 1 2 3 and 1 3 2. So clearly this element is a group. This A3 itself will form a group. So you can see I is here, I is identity exists, and you just take two elements 1 2 3 1 3 2. Now you just multiply, what you will have. So 1 2 3 means, so 1 2 3 means 1 goes to 2, 2 goes to 3, 3 goes to 1. So if we multiply this, we will have 1 goes to 2, 2 goes to 3, 2 goes to 3, 3 goes to 1, 3 goes to 1, 1 goes to 2. This is nothing but 1 3 2. So therefore this element belongs to H. Let us say this to be H. So therefore it is closed, and again it is associative also. So ID exists, and inverse also exists. So what is the inverse of 1, 2, 3? So inverse of 1, 2, 3 means you have to permute with itself. You have to permute with itself. So 1, 2, 3 means 1 goes to 2. So 2, 3, 1. So you have to permute with itself. So this is 1 goes to 2, 2 goes to 3, 2 goes to 3, 3 goes to 1. Actually, I made some mistake, I think. So 1, 2, 3. 1, 2, 3 means 2, 3, 1. And taken this element, right? So 1, 3, 2. So 1, 3, 2 means 1 goes to 3, 3 goes to 2, 2 goes to 1. So if you make this, so 1 goes to 2, 2 goes to 1, 2 goes to 3, 3 goes to 2, 3 goes to 1, 1 goes to 3. So this is equal to I. So belongs to H. Anyway, whatever elements you take, you just permute them, it will be in group G. And what is the inverse of 1, 2, 3? You have to permute itself. So 1 goes to 2, 2 goes to 3. I am making the two elements to be this and this, right? So this and this. So if I permute, I will get I, so which is in G. So therefore it is closed. And inverse of 1, 2, 3 is you have to permute itself. So 1 goes to 2, 2 goes to 3, 2 goes to 3, 3 goes to 1, 3 goes to 1, 1 goes to 2. So which is nothing but 1, 3, 2. So 1, 3, 2 is in H. So therefore inverse of 1, 2, 3 is 1, 3, 2, and this 1, 3, 2 belongs to H. So therefore similarly inverse exists for each element. So therefore this itself a group, right? This itself a group. So therefore it is a subgroup of A3. So similarly, if G is equal to Sn, then H is equal to An will be a subgroup. Set of all even permutations on n symbols will always be a subgroup of Sn. So these are some examples of subgroups. Now we will see algebra of complexes of a group, right? Multiplication of complexes. So now we will prove some theorems. So there are some three basic theorems, and then we will move on to important theorem, that is necessary and sufficient condition for a subset to be a subgroup. So before that so first we have started with defining a subgroup, and then we have seen some examples of a subgroup. Now we are going to see some basic theorems on subgroups. So some basic theorems on subgroups. So let H and K be any two, let H be any complex of G. Sorry, theorem 1. Let H and K, if H and K are any two complexes of a group G, or any two complex of a group G, then HK whole inverse is same as K inverse H inverse. So remember, here H and K are not subgroups, they are complex of a group. Remember, H and K are not subgroups, it is nothing a subset of a group, right? So if I have a G here, so this is a subset. I am taking two subsets H and K. Remember, there is a difference between subset and subgroup. So if this subset is a group, then we call it as a subgroup. But so far, H and K are not subgroups, it is a subset. So if H and K are into complex of a group G, then HK whole inverse is same as K inverse H inverse. So whenever in a modern algebra, if you want to prove the equality, what we will do is, so first we will show that this is contained in this, and second we will show this is contained in this. So therefore both are equal. This is the idea that we will follow whenever we have to prove that two are equal, right? So this is contained in this and this is contained in this, so therefore both are equal. That is the idea we will be proving to prove equality, right? Yes. Now we need to prove HK whole inverse is equal to K inverse X inverse. So let X belongs to, so let X belongs to HK whole inverse. Let X belongs to HK whole inverse. Now every element, now I can write X as some small HK whole inverse, right? So I'm taking an element. I'm taking an element small x in the group capital H comma k whole inverse. Then every element can be written as small h comma k whole inverse, where this small h belongs to capital H and this small k belongs to capital K. Small k belongs to capital K. Now this I can write this as k inverse h inverse. Remember, this is different from this. These two are elements. Here these two are subsets. There is a difference between, this is a single element, this is a single element, but this is a subset. So I can write the element as k inverse h inverse, k inverse h inverse. So this element will be in k inverse h inverse, right? This element will be in capital K inverse h inverse. So where I have chosen x, I have chosen x in the left hand side, and I have proved that that element is also in right hand side. So this implies I have taken x in hk whole inverse, and I have proved that this element is also in k inverse h inverse. Therefore hk whole inverse is contained in k inverse h inverse. Now I am going to choose an element x from the right hand side, and I am going to prove that it is also in left hand side. So let us take y. Let y belongs to k inverse h inverse. I am taking an element y belongs to k inverse h inverse. Then I can write y as some small k inverse, some small h inverse. So this is an element, so I can write this as small hk whole inverse. So this element will be in hk whole inverse, right? So therefore I have taken an element y in the right hand side, and I have proved that element is also in left hand side. So therefore this implies I have taken y, where I have taken y in right hand side. So this implies k inverse h inverse, k inverse h inverse is contained in hk whole inverse, hk whole inverse. So you mark this as 1, you mark this as 2. So from 1 and 2, this is contained in this and that is contained in this. So therefore both has to be equal. So from 1 and 2, hk whole inverse is equal to k inverse h inverse. That's it, right? This is a theorem, basic theorems. So I'll move on to the next theorem. So theorem 2. So theorem 2, if H is any subgroup of G, if H is any subgroup of G, if H is any subgroup of G, then H inverse is same as H. H inverse is same as H. Show that converse is not true. Converse is not true. Converse is not true. So proof. So if H is any subgroup, so let us say this is G and this is H. And this is now it is given that it is a subgroup. That means H itself a group. H itself a group. Now we need to prove that H inverse is same as H. So first we define H inverse is equal to set of all inverse. Set of all inverse such that this H belongs to capital H. Right? So for example, if G is equal to 1 minus 1 I minus I, so we already verified that 1 and minus 1 are subgroups. Now what about H inverse? What about H inverse? It is a set of all H inverse such that this H belongs to capital H. So this set contains 1 inverse and this set contains minus 1 inverse, right? So you can see what is the inverse of 1? It will be 1 again. Inverse of minus 1 is minus 1. Now you can see both H and H inverse are same. That is the one we need to prove. H inverse is the set containing all its inverse element. So if H is 1 and minus 1, so H inverse is 1 inverse and minus 1 inverse. So therefore we can see H inverse is also same as H. So if H is any subgroup of G, then H inverse is same as H, and H inverse is a set containing all the inverse of H, and we need to prove that both are equal. But converse is not true. Suppose if this happens, then H need not be a subgroup. So we will move on to converse part later. Suppose we will prove that H inverse is same as capital H. So we know that H inverse is set of all inverse of H such that this H belongs to capital H. Now let H inverse be any arbitrary element. So H inverse be any arbitrary element of capital H inverse. So I am taking some element H inverse be any arbitrary element. For example, H inverse can be -1 or 1. So I am taking H inverse be any arbitrary element of H inverse. Then H belongs to H. Right? So H inverse be any arbitrary element, and we know that this H belongs to S. This is by defining H inverse, right? So H inverse be any arbitrary element of the capital H inverse, then small h belongs to capital H. So therefore small h belongs to F. So since we know that H is already a subgroup, right? H is already a subgroup. So what can you say about this element? This element has an inverse, and that inverse will be in H, right or not? So H inverse is an arbitrary element in capital H inverse, and H inverse means H belongs to capital H, and this capital H is already a subgroup. So what can you say about H inverse? So H inverse also belongs to H. This is by definition of subgroup, that inverse also will be in that set. So therefore H inverse belongs to H. So where I have chosen H inverse? I have chosen H inverse in capital H inverse, but now I have shown that capital H, this small h inverse also in capital H. So therefore I have taken capital H inverse in capital H inverse. So therefore this is containing H, right? So similarly, what I am doing is I am taking an element here and I am showing that element is also here. Now I am going to take an element from H and I am going to show that this element is also in capital H inverse, right? So this is the first. Now I'm going to take an element from capital H, right? So this is by taking an element from LHS and proving that element is also in RHS. Now I am going to take by taking an element in RHS. I am going to show that element is also contained in LHS. Now let us say this H belongs to capital H. Now here what I have shown, now I have taken H inverse in capital H inverse and I have shown that this small h inverse is also in capital H. Now I am going to take left hand side. Now H belongs to H. What I need to prove that this H is also in capital H inverse. This H now since this H belongs to H, so since H is a subgroup, so therefore H inverse belongs to H. Now H inverse belongs to F. What can I say about inverse for H inverse? That also will be in so taking inverse on both sides. So H inverse whole inverse will be belong to capital H inverse. So what we have showed is, so H inverse is H. So therefore this belongs to H inverse. I have taken an element H in H and I have proved that this is also in capital H inverse. So therefore this H is chosen from capital H. So therefore H is contained in H inverse. So from 1 and 2, capital H is same as capital H inverse. So whenever you have to prove the inequality, you have to take one element from LHS and you have to prove that element is also in RHS, and you have to take one element from RHS and you have to prove that element is also in LHS. Now we need to show that the converse is not true. Converse is not true means, so if whenever H inverse is equal to H need not be a subgroup. If H is a subgroup, then H inverse will be same as H, but the converse is not true. Converse. So that is what we need to prove. So to prove, if H inverse is same as H, then H need not be a subgroup. Need not be a subgroup. This is the one we need to prove. If H inverse is equal to H, then H need not be a subgroup. Now we will whenever you have not to prove, we have to give a counter example. So we will give counter example. Now let us take an element H. Now let us take G to be 1 minus 1 I minus I, right. So let us take H is equal to minus 1, H is equal to minus 1. Now let us restrict that G is equal to 1 minus 1, that is a set of all second root of unity. Now wait, let us take H to be equal to minus 1. Now what about H inverse? H inverse is also minus 1, right, because minus 1 into something has to give me 1, this element is also minus 1. So therefore H is same as H inverse, but H is not a subgroup. H is not a subgroup. Why? Because H does not contain identity, because and ID is 1, but this is not a subgroup, this is a subset alone, but this is not a subgroup because H does not contain E, which is 1 here. So therefore H is same as H inverse, but H need not be a subgroup. So converse is not true. Converse is not true. So the third theorem, if H is any subgroup of G, then capital H is same as H. H into H is same as H. So theorem 3, if H is any subgroup of G, then H is same as H. H is same as H. Right, so first we will define HH. What is defined HH? So what is HH? Set of all X, set of all X belongs to G, set of all X belongs to G, set of all X belongs to G, that X is equal to HH. X is equal to HH, and the small h belongs to capital H, and this small h belongs to capital H. Right, this is the definition part. Capital H into H, set of all X in G, such that X can be written as H into H. Now we will define that, so we will prove that H into H is same as H. Again, what you have to do? You have to take one element from LHS and you have to prove that that element is also in RHS, and you have to take one element from RHS and you have to prove that element is also in LHS. Now I am taking one element LHS, so let H1 H2 belongs to capital H, capital HH. So I am taking one element from capital HH, where this H1 belongs to capital H and this H2 belongs to capital H again. Suppose if I have K, then H2 belongs to K, but since both are HH, first element is also in H, second element is also in H. Suppose if I have HK, then first element will be in H, second element will be in K, but here we have both to be equal to H. So H1 belongs to capital H and H2 belongs to capital H. Now I have taken one element from LHS, I need to prove that H1 H2 is also in H. H1 H2 is also in H. Now what H1 and H2 belongs to H, right? So that is H1 and H2 are in H, and this H is a subgroup. This H is a, there can be some other elements also, but surely H1 and H2 are in H. So H is a subgroup. H is a subgroup. So by closure, what can you say about H1 into H2? Will it be in H or not? Will it be in H or not? It will be in H, right? Because it is a subgroup. So subgroup means it itself a group. So therefore, by closure property, this element is also in H. So I have taken H1 and H2 in capital HH. I have proved that H1 and H2 is also in H. So where I have taken H1 and H2, I have taken HH. So H is contained in H. Now we will prove another part. I will take one element from RHS. So let H belongs to capital H, right? H belongs to capital H. Now I need to prove that this small h is also belongs to capital HH. Small h also belongs to capital HH. Now I can write this H as H into E, because H is a subgroup, ID exists, so I can write H as H into E. Now HE belongs to HH, HE belongs to HH, right or not? This HE belongs to H into H. Why? I can write H as H into E, and I can, what are the elements of HH? It contains all HH, and this small h belongs to capital H, and this small h also belongs to capital H. Surely this element will be in capital H, right? So I can see our small h is H and another small h is E. So therefore H into E will be in HH. So H into E is nothing but H. So therefore H belongs to HH. Where I have taken H? I have taken H from capital H. So therefore H is contained in HH. H is contained in HH. So from this and this, H is equal to HH, right? So I can write H as H into E. So whenever writing this as a product of two elements, it will be in HH. So therefore both are equal. So these are the three fundamental theorems. And the criterion, it's a very important theorem, that criterion for a complex to be a subgroup. So when a subset will be a subgroup. So we have again theorem 1 and theorem 2. And then we will do corollary 1, theorem 3, theorem 3, and then one corollary. Okay. I'll try to complete subgroups today, right? I try to complete subgroups today. The non subset H of group is criterion for a. So I'm going to prove three theorems again. So that this is a criteria. So if you want to prove that H is a subgroup, it will take time, right? So if G is a group, then subset will be a subgroup. If H itself a group, so it will take time, right? So we have to verify whether H is closed, H is associative, H has identity, H has inverse. So it will take time, right? So what they are doing is we are trying to restrict that condition. We are trying to restrict that condition. So there are two theorems, right? So there are two theorems and one corollary, and then some examples, and then criterion for subgroup to subgroups. Okay, so we will be cut shorting that condition. That is, if you want to prove H is a subgroup, we need to prove H is closed, H is associative, H has inverse, H has identity. Now we are trying to cut short that condition, right? So this is this is a criterion for a complex to be subgroup. Let us call this as theorem 4. Theorem 4. So a non-empty subset H of a group G, a non-empty subset H of a group G is a subgroup. If and only if. So whenever you have if and only if, you have to study the theorem importantly. So I am restricting only to two conditions. So it is enough for us to H to be closed and inverse, right? So you don't need to verify associativity. So whenever you have closeness, it will become associative for a subset, and for ID also it is unnecessary, right? So if and only if A belongs to H, B belongs to H, then AB belongs to H. AB belongs to H, and if A belongs to H, this implies A inverse is also in H. So, first we have started with 4 conditions. Now we are restricting ourselves to 2 conditions, that if A belongs to H, B belongs to H, AB should also in H, and if A belongs to H, A inverse should also in H. So, if these 2 conditions satisfies, then it will be a subgroup. It is an if not if condition, right? It will be if not condition. So, it is very important. So, when you just only check whether that subset is closed and every element has inverse, and that inverse element should also in H. So, we are restricting the conditions from 4 to 2. So, we will prove this, right? So, this is G, this is H, and this will be a subgroup if it is closed and every element has inverse in capital H itself. So, we are restricting to 2 conditions. Now, we belongs to H, A inverse belongs to H, right? The condition is here. Now we will prove. Now we will assume that it is a subgroup, and we will prove that A inverse belongs to H. Assume H is a subgroup. What we need to prove? To prove 1 and 2. So I just like 1 and 2. 1 and 2 are this. So if this happens, we need to prove these 2 conditions, and in the later part we will be assuming these 2 conditions, and we will be proving that it is a subgroup. So assume that it is a subgroup. Now we need to prove 2 conditions. Now first we will prove that A inverse belongs to H, and we will prove that AB is also in H. Now H is a subgroup, right? H is a subgroup. So now we will prove one by one. So H is a subgroup, right? So H is a subgroup. So let us take 2 elements. Let us take 2 elements. A comma B belongs to H. So what can I say about AB? So since it is a subgroup, clearly AB should also in H. So therefore we have put first condition, right? So if A belongs to H, B belongs to H, AB belongs to H. So since we have assumed that it is a subgroup, AB belongs to H. Now we need to prove A inverse belongs to H. Now we already assumed that A is a subgroup, right? So since let A belongs to H. Let A belongs to H. And we have assumed that since H is a subgroup, that A inverse is also in H because of subgroup criteria. So therefore A inverse also belongs to H. So therefore we have proved the first part. So if H is a subgroup, then these 2 are natural. Now what can you say about? We will assume the opposite side. Now we will assume that 1 and 2, and we will prove that it's a subgroup. So we have proved the first part. So now we will prove that second part. So assume 1 and 2. Assume 1 and 2. Now we need to prove that H is a subgroup. That means H is a subgroup means we need to prove H itself a group. H itself a group. H itself a group. So now we need to prove that H itself a group. That means we need to show that H is closed, H is associative, H has ID element, and H has inverse elements. H has inverse elements. Now we have assumed these 2 conditions, right? A belongs to H, B belongs to H means AB belongs to H, and A belongs to H means A inverse belongs to H. Now we will prove that H itself a group. So first is closed. So H is closed. H is closed. Let us take 2 elements in. Let us take 2 elements in H. So what can I say about AB? It will be in H by assumption. By assumption. So AB belongs to H. So therefore it is closed. Now associative. Now we are taking a subset H of a group G, right? So since group G is associative, that subset will also be associative, right? Since G is associative, now the elements in H are in G, right? So since G is associative, G is a big group. We have know that G is associative. So if G is associative means we are taking only some elements and calling that as H. So surely this element will also be associative, right? So big set is associative means that means all the elements have associative property. Now we are taking only small elements from that set. So therefore the elements in H are in G. So therefore H is associative since G is a group. Now identity. We need to prove that H has ID element. Now since G is a group, let E belongs to G. So G is a group, let E belongs to G. Now there is one theorem that if E is the identity of G, then same ID will be for subgroup also. There is no different ID for subgroup and group, right? So since G is a group, E belongs to G. So therefore we know that a subgroup should also have same identity. Subgroup should also have same identity. So therefore E belongs to H. Now we need to prove inverse, and again by assumption A belongs to H means A inverse belongs to H, right? This is our assumption. So inverse. So let A belongs to H, this implies A inverse belongs to H by the assumption 2. So therefore if H is a subgroup, then these two conditions are enough to claim that H is a subgroup. So now we will move on to the important condition. Now first we have started with 4 conditions, right? So in order to, if you want to prove that H is a subgroup, we need to check 4 conditions. Now we are restricting that to 2 conditions. Now in the next theorem, we are going to restrict only to 1 condition. So theorem 5, very important theorem. So an important characteristic property of subgroup. So theorem 6, an important the theorem 6 itself, an important characteristics property of a subgroup. So in exam they can ask, state and prove the characteristic property of a subgroup. So a necessary and sufficient condition for a non-empty set, very important theorem. A necessary and sufficient condition, for a non-empty subset H, for a non-empty subset H of a group G, is a subgroup is that if A belongs to H, B belongs to H, then AB inverse belongs to H. So if this condition alone satisfies, then H will be a subgroup, right? So what this says is, this is G, this is H. So very first, when you are defining subgroup, we have said that this H has to be closed, associative, ID, inverse. Now in the previous theorem I have said that it is not that we need to check 4 conditions. It is enough to check only 2 conditions, which is closed and inverse. But now what I am telling is, it is enough only to check this condition. You just take 2 elements in G and you just check whether AB inverse is also in H. So if that happens for all AB, then it will be a subgroup. Just take some element A and you just check B. Now you find the inverse of B and you multiply AB. So it is nothing but operation. So whatever operation you are choosing, you just operate AB inverse. If you are choosing plus to be an operation, this is A plus B inverse. If you are choosing operation to be modulo, it will be A modulo B inverse. So if this condition alone satisfies, then it will be a subgroup. So first we started 4 and 2, now we are restricted to one condition, which is the necessary and sufficient condition for a non-empty subset H of a group G is a subgroup, is that A belongs to H, B belongs to H, means AB inverse belongs to H. Now we will assume that it is a subgroup, and we will prove this condition. So we mean subgroup if and only if A belongs to H, B belongs to H, AB inverse belongs to H. Now we will assume that H is a subgroup. So what we need to prove? To prove if A belongs to H, B belongs to H, this implies AB inverse belongs to H. This is the one we need to prove, right? Yes, this is the one we need to prove. Now H is a subgroup. So since H is a subgroup, now I'm going to take two elements. Let us take A belongs to H, B belongs to H. Now what can I say about B inverse? B inverse belongs to H, because H is a subgroup, so inverse has to be in that group. Now we have said that we have taken AB in H, and we have proved that B inverse is also in H. Now what about A into B inverse? So since H is a subgroup, it is closed, right? So if I take two elements to be A and B inverse, what about AB inverse? It will be also in H, because since H is a subgroup, so closed. That is closure property will be satisfied. So therefore AB inverse belongs to H. So I assumed that H is a subgroup, and I have proved that if A and B are in H, AB inverse belongs to H. Now we need to prove the converse part, that is a later part. That is, I am assuming that A belongs to H, B belongs to H, means AB inverse belongs to H. Now we need to prove that H is a subgroup, right? So this is assumption, this is assume. Now this is to prove. Now what is the assumption? If two elements are in H, then AB inverse is also in H. Now what I need to prove? H is a subgroup. That is where we need to prove that it is closed, it is associative, and it has identity, and it has inverse. Now we will prove one by one. H is closed. Or else what you can do is, if you want to use the previous theorem, you can use that previous result, and it is enough to prove only closed and inverse. But we don't use the previous theorem. We will prove the basic definition. We will prove that H is a group. So H is closed. So that means if A belongs to H, B belongs to H, I need to prove that AB inverse is AB belongs to H. AB belongs to H. Now what is the assumption? By assumption, A belongs to H, B belongs to H, means AB inverse belongs to H. Now what can I say about A belongs to H, B belongs to H? This means B inverse also in H, right? So if A belongs to H, B belongs to H, B inverse belongs to H, then AB inverse belongs to H, right? This is our assumption, right? So A belongs to H, B belongs to H, B inverse will also be in H. Okay. Now we need to prove that AB belongs to H, right? Yes. Now I can write AB as A into B inverse whole inverse, right? I can write AB as A into B inverse whole inverse. Why? Because B inverse is in H and inverse also exists for that element. This is same as AB and this belongs to H. This is equal to AB and this belongs to H. Right? I need to prove AB belongs to H. So I can write always B as B inverse whole inverse. Right? B inverse whole inverse. And since this B inverse is in H, I can write like this. So therefore, AB belongs to H. And again, associativity. You don't need to prove associativity. What you can do is, since the elements of H are in G, the elements of H are in G, and since G is a group, this is the one we wrote for the previous theorem also, and since G is a group, it is associative. G is associative, and H is we are only taking some elements, so therefore H is also associative, right? So G is associative, big set is associative. Now that means every element is associative. We are only taking some elements from that, so therefore it will be associative. Therefore H is associative. Now we need to prove H as identity element. H as identity element. Now we have A belongs to H, B belongs to H. A belongs to H, B belongs to H. Now what can this A belongs to H means? A inverse belongs to H. A inverse belongs to H. Now what can you say about A into A inverse? A into A inverse, this will be in H. What is A into A inverse? E. So therefore E belongs to H. So therefore E belongs to H. P inverse belongs to H, right? Yes. Now we need to prove that it has inverse. Now what about inverse? Now that A belongs to H. Now we need to prove A inverse is also in H. Now what is the assumption? If A belongs to H, B belongs to H, then AB inverse belongs to H, right? So suppose we already know that E belongs to H. Now we are assuming that A belongs to H, right? Suppose we know that E belongs to H, and let I am taking A belongs to H. So whenever you are taking two elements, AB inverse will be in H. This is our assumption. Now I am taking two elements to be E and A. So what I can conclude? E into A inverse belongs to H, right? So whenever you take two elements, AB inverse will be in H. This is our assumption. Now I am taking two elements to be E and A. So therefore the product of this element will be in H. So therefore E inverse belongs. What is E into A inverse? It is nothing but A inverse. Therefore A inverse belongs to H. So therefore this is the group, right? Yes. Right? Yes. And very important is that we have taken AB inverse, right? AB inverse. Now suppose if the operation addition, AB inverse will be A minus B, right? You have to be careful, right? So B inverse is the operation that we are defining, right? Suppose if the operation is addition, B inverse is minus B, right? Yes. Now we have proved this theorem. Important remark. The above theorem gives us a very important characterization of a subgroup. Whenever we are required to show that a non-empty subset H of a group G is a subgroup, we should make use of this theorem. Thus, we should take any two arbitrary elements AB belongs to H, and we should try to show that AB inverse belongs to H. If we are able to show that if AB belongs to H implies AB inverse belongs to H, it is sufficient to conclude H is a subgroup of G. Right, very important. I will repeat an important remark. So, whenever from now on, if you have to prove that a subset is a subgroup, you have to take two elements in that subgroup and you have to prove that AB inverse belongs to H. The above theorem gives us a very important characterization of a subgroup. Whenever we are required to show that a non-empty subset H of a group G is a subgroup of G, we should make use of this theorem. Thus, we should take any two arbitrary elements AB belongs to H and we should try to show that AB inverse belongs to H. If we are able to show, it is sufficient to conclude that H is a subgroup of G. Right? Yes. So, there are two corollaries, it's a two line proof. You can just verify, go through that, page number 142. Now, I will give some example. So, there are some examples, and we will give some for example. Again, actually all the examples we have seen. Okay, so example 1, let G be the additive group of all integers and H be a subset consisting of all positive integers. Obviously, H is close to disparate addition, but H is not a subgroup since 0 is not in G. So, they are giving the condition that actually we have discussed these examples, right. So, let H be additive subgroup of G. If I take H to be the set of all integers with respect to addition, if I take a subgroup to be positive integers, it is not subgroup because positive integer does not contain 0. Therefore, there is no ID element in the subgroup. So, therefore, it is not a subgroup. That is the one they are saying. Yes, actually, we have seen all these examples. Now, very important theorem we are going to prove that criterion for product of two subgroups to be a subgroups. So, if I have subgroup, if I have another subgroup, then that product will be a subgroup, right. So, if I have H and K be two subgroup, can I say HK is a subgroup? That is what we are going to prove, right. So, what we are going to do is we are going to have two subgroups. Now, I am going to verify whether H into K is subgroup or not, or when it will be a subgroup. What about H intersection K? What about H union K? So, these are the three we are going to discuss. These are the three that we are going to discuss. That is, I will repeat. If I have two subgroups, what can I say about H into K? What can I say about H intersection K? And what can I say about H union K? Will it be a subgroup or not? These are the three conditions, that we are going to discuss now, right. And then after discussing that, they have given some solved example. So, there are 8 problems. I'll just prove 3 to 4 and then you will just take towards exercise. Now, before that we will discuss about if I have two subgroups, what can I say about the product of two subgroups. So, I will complete some groups today, and the courses and Laplace's theorem I will send recorded videos. So, you have to go through that, and in the next class we will be taking cyclic groups. 1 hour 4 minutes. Okay. Criterion for product of two subgroups to be a subgroups. This is theorem 7 or 8. Okay. So, criterion for product of two subgroups to be a subgroups. Criterion for product of two subgroups to be a subgroup. So, when the product of two subgroups will be a subgroup, that is what we are going to discuss now. So theorem, if H and K be two subgroups of a group G, so if this is a statement, if H and K be two subgroups of a group G, two subgroups of a group G, then HK is a subgroup, then HK is a subgroup, HK is a subgroup if and only if. So this is same as if and only if, both are same, right? IFF, or if I use this condition, if I use this symbol. So HK is subgroup if and only if HK is equal to KH. Important theorem. HK is equal to KH. Right? So here we have G, here we have H, here we have K. So what about HK? So HK will be a subgroup if HK is equal to KH. If HK is equal to KH, and we know how the elements of HK will be. The elements of HK will be small hk, and this small h belongs to capital H, and this small k belongs to capital K. So these are all the elements of HK, right? So here the operation is the operation that we are choosing. Whenever if there is a gap, that means you need to plug in the operation that you are using. Now we will prove this, right? So it's a if and only if condition. Now let us assume that H and K be two subgroups of a group G. We will prove that, we will assume that HK is a subgroup. We will prove that HK is equal to KH, and we will prove the vice versa. Now assume HK is equal to KH. Assume HK is equal to KH. What I need to prove? HK is a subgroup. HK is a subgroup. So I am assuming that HK is equal to KH, and I need to prove that HK is a subgroup, right? And in order to prove HK is a subgroup, by necessary supposition condition, it is enough to prove that AB inverse belongs to this set, right? So I need to prove this. I need to prove this is a subgroup. So for that, what I am going to do is I am going to take a small. I am going to take an element HK, and I am going to prove that okay. I am going to prove that HK into HK inverse, HK into HK inverse is equal to HK. This is the one we need to prove, right? In order to prove HK is a subgroup, it is sufficient to prove that HK into HK inverse is same as HK. Okay. Okay. So what we will do is we need to prove HK is a subgroup, right? HK is a subgroup. Now we need to prove HK is a subgroup. So that is to prove HK into HK whole inverse is same as HK. This is the one we are going to prove, right? This is the one we are going to prove. Why? So we know that if AB inverse is in H, it will be a subgroup. I am taking A to be HK and B to be HK again, right? It is not that A and B has to be distinct, right? So if you take any two elements, AB inverse belongs to H. I am taking both the elements to be HK. So HK inverse will be HK. So if I say this condition, it will be a subgroup, right? So I am assuming that HK is equal to KH, and I need to prove that HK into HK whole inverse is equal to HK. So if we prove this, it will be done, right? So we will take this and we will prove that this is equal to HK. So HK into HK whole inverse. So we will take this. Now we have assumed that HK is equal to KH. Now I can write this as HK into K inverse H inverse by theorem 1. right? So just go through the theorem 1 that I solved in the very beginning of the video, that HK whole inverse is same as K inverse H inverse. Now I can write this as H into K inverse into H inverse. So K into K inverse is I, because why? Because K is a subgroup. So K is this K is a subgroup. So therefore we know that if K is a subgroup, then H is same as H inverse. Therefore H into H inverse is equal to E. So therefore H into yes, K into K inverse is nothing but K, right? K into K is nothing but K. Why? So we have proved the theorem that so we will recall the theorem that we proved earlier. If H is a subgroup, then H inverse is same as H. H inverse is same as H, right? So H inverse is same as H, and H into H is same as H. You just go through theorem 2 and theorem 3 that we proved in the very beginning of the video. That K we will move by some other method. So K inverse is same as K, right? If K is a subgroup, then okay. Now I can write this as K into K H inverse, right? So K inverse is same as K by theorem 2. And by theorem 3, what is theorem 3? If H is a subgroup, then H into H is same as H. Now here K is a subgroup, so therefore K into K is same as K. So therefore H into K H inverse. This is by theorem 3. So you just go through the first 3 theorems. The first theorem tells that HK inverse is equal to K inverse H inverse. Second theorem tells that K inverse is same as K, and third theorem tells that K into K is same as K. So there we have proved for H, now we are proving for K. Right? So this is HK H inverse. Now what I am going to do is I am going to combine HK and I am going to keep HK H inverse as it is, and we know that HK is equal to KH by assumption, right? By assumption. This is by assumption. So now I can combine H and H inverse, and again H into H inverse is same as H by theorem 2. H into H is same as H by theorem 3. So we have started with HK inverse. We have proved that it is equal to HK. So therefore it is HK is a subgroup. Right? So just go through theorem 1, 2, 3 before proving this theorem. So I will repeat. We have used theorem 1, theorem 2, theorem 3, and we have interchanged using the assumption, and again I am using theorem 2 and theorem 3 to prove that HK is a subgroup. Now I am going to assume that HK is a subgroup, and I am going to prove HK is equal to KH, right? Conversely, suppose HK is a subgroup. So conversely, if this is assumption and this is to prove. Now if by assumption HK is a subgroup, now by theorem 2, so you just have to quote the theorem, right? So by theorem 2, what we have proved, if H is a subgroup, then H inverse is same as H. This is theorem 2, right? So just go through the theorem, and I think it is theorem 2. So H inverse is same as H. So what can you say about HK inverse? It is same as HK, right? HK inverse is same as HK. Now by theorem 1 I can write this as K inverse H inverse is equal to HK. We have assumed that HK is a subgroup. We have assumed that HK is a subgroup. Now what about K inverse? It is K again by theorem 2. What about H inverse? It is H again. So we can write this because HK is a subgroup by assumption. So therefore inverse exists. So therefore K inverse H inverse. K is equal to HK. That's it. Okay. So just go through the previous theorem. You can easily make proof in your own. Right? Okay. So now we will move on to theorem 8. So this is the criteria for the product of two subgroups to be a subgroup. So first discussion that if H and K are two subgroup, then HK is a subgroup if and only if HK is equal to KH. In general, it will not be true. If this happens, then HK will be a subgroup. Now we are going to discuss about if H1 and H2 are two subgroups, what about H1 intersection H2? What about H1 intersection H2? That is the one we are going to discuss now. And what about H1 union H2? H1 union H2. Theorem 8. Theorem 8, intersection of subgroups. Intersection of subgroups. So if H1 and H2 are two subgroups, if H1 and H2 are two subgroups, then H1 intersection H2 is also a subgroup. Is also a subgroup. So for HK there is some restriction that HK has to be equal to KH, but for intersection there is no restriction that H1 intersection H2 will always be a subgroup. This is if and then, right? If this happens, it will happen. If this happens, this is not necessarily be true. So we will assume that H1 HK are two subgroup and it is not if and only if condition. So we will assume this and we will prove this. So let H1 and H2 be two subgroups. So what I need to prove? H1 intersection H2 is also a subgroup. That is, what I need to prove is I need to take two elements in H1. This is to prove. I take two elements in H1 intersection H2 and I need to prove that AB inverse belongs to H1 intersection H2. This is the one we need to prove, right? H1 intersection H2 is a set again. This is a set. So this is a set, right? And in this set, I am taking two elements AB, and I need to prove AB inverse belongs to H1 intersection H2, right? Yes. Now if two elements belongs to this, I need to prove this also belongs to H, right? So if A belongs to H1 intersection H2, B belongs to H1 intersection H2. Now A belongs to H1 intersection H2. That means A belongs to H1 and A belongs to H2. This is quite natural, right? So this element is in intersection of both. That means it has to be present in both the set. So H belongs to H1 and A belongs to E2. What can I say about B? B belongs to H1 and B belongs to H2. B belongs to H2. Now A belongs to H1. A belongs to H1. So we have already assumed that H and H2 are two subgroups. Now what can I say about A inverse? What can I say about A inverse? What can I say about A inverse? So A okay. Now we have A belongs to H1 B belongs to H1, right? We have A belongs to H1, B belongs to H1, right? So similarly, we have A belongs to H2, B belongs to H2, right? So we have A belongs to H1, B belongs to H1, A belongs to H2, B belongs to H2. Now H1 is a group, right? H1 is a subgroup. H1 is a subgroup. So this implies AB inverse belongs to H1. Can I say A belongs to H1, B belongs to H1? From this we have verified H1 is a subgroup. So therefore AB inverse has to be in H1. So again AB inverse has to be in H2. AB inverse has to be in H2. So AB inverse belongs to H1, AB inverse belongs to H2. So this element is in H1 also, this element is H2 also. So can I say AB inverse belongs to H1 intersection H2? Can I say? So this element is in H1. So AB inverse is in H1 and AB inverse also in H2. So when I make an intersection of H1 and H2, surely this element will be in this set, right? Because it is in both the set. So therefore AB inverse belongs to H. This is what we need to prove, right? So we need to prove AB inverse belongs to H1 intersection H2. So therefore H1 intersection H2 is a subgroup. That's it, right? Important proof. So short proof but important proof, right? So AB inverse belongs to H1. So therefore we have taken, we have taken A in H1 intersection H2, we have taken B in H1 intersection H2, we have shown that AB inverse is in H1 intersection H2. So this implies H1 intersection H2 is a subgroup. Now we have only taken two subgroups. It is also true for arbitrary intersection of subgroups. The intersection of any family of subgroup is a subgroup. Intersection of any family, that is if H1, H2, H3, H4, H5, H6, H10 are subgroups, then H1 intersection H2 intersection H3 intersection up to H intersection 10 will also be a subgroup, right? So I think you can prove this very easily. So it is just an extension of this, right? It is just a extension of this. So what this says is the arbitrary intersection of subgroup is again a subgroup. The intersection of any family of subgroup is a subgroup. So if you understand this proof, you just replace A to be equal to AI, B to be equal to BI, and this to be equal to intersection of HI. So I think you can easily follow the proof. So yeah, you just practice it, right? So I'll just tell orally. So you just go through the page number 145. Theorem intersection of family of subgroups. Intersection of family of subgroups is a subgroup. Is a subgroup. So what I need to prove is if T belongs to so what I need to prove is if H1, H2 up to Hn are subgroups, then intersection of Hi, I belongs to 1 to n, is also a subgroup. So a similar proof. So instead of taking let us take some let. So just follow the same technique here. So let A belongs to H1 intersection H2 up to intersection Hn, and let us take what I need to prove. if A belongs to, what I need to prove? So I'll just give you a rough proof. We will write the proof in our own. We will follow different proof. So just take some element in intersection of HI and take some other element in the intersection of HI. You need to prove AB inverse belongs to intersection of HI. This intersection, right? Intersection. Now, same method, right? So instead of we are just extending, that's it. Now A belongs to intersection of HI, B belongs to intersection of HI. That means A belongs to H1, intersection of HI is nothing but H1 intersection S2 up to Hn, and this B belongs to H1 intersection S2 up to Hn. Now if A belongs to H1, S2, S3, Hn means this implies A belongs to H1, A belongs to S2, A belongs to S3 up to A belongs to Hn. Now what can I say about B? B belongs to H1, B belongs to S2, B belongs to S3 up to B belongs to Hn. Now when you combine these two, I can say A comma B belongs to H1, again A comma B belongs to H2, combine these two, A comma B belongs to H3, A comma B belongs to H4 up to, okay, up to A comma B belongs to Hn. So if AB belongs to H1 and since H1 is a subgroup, AB inverse belongs to H1, AB inverse belongs to S2, AB inverse belongs to S3, right? Similar proof, I am just extending. You are following a different proof, I am writing in my proof in my own. So again, what can I say about AB inverse? It is also in Hn. Now AB inverse is in H1, AB inverse is in H2, AB inverse is in H3. Can I say AB inverse belongs to intersection of HI? If I make intersection, it will be in H. So can I say intersection of HI? Because this element is H1, this element is in H2, this element is in S3 and this element is in Hn. So therefore this element is in HI. This is the one we need to prove, right? Elementary proof. So they have followed different proof here. Now we will write proof in our own. So we will write this proof, right? So we have shown that intersection of family of subgroup is a subgroup. Intersection of family of subgroup is a subgroup. So so next theorem is union, right? So just go through the theorem. We need to show that union of two subgroup is not necessarily a subgroup. Is not necessarily a subgroup. We need to prove that union is not a subgroup. So I'll just quickly fill the ink. Now we need to show that if H1 and S2 are subgroup, H1 union S2 need not be a subgroup. So that is, we need to give one counter example, right? Actually, you can write proof in your own if you understand the definitions well. So last theorem that we are going to do in subgroups, and then we will see some problems, and then we will wind up subgroups. So I think you understand this proof. So it is in page number 146, the PDF that I have sent the union of subgroups is not a subgroup. The union of two subgroups, so theorem, the union of two subgroups is not necessarily a subgroup, is not necessarily a subgroup for proof. So in order to prove not, we will give some counter example. So we will produce two subgroups and we will show that C, union is not a subgroup. So let us take a subgroup G. Let us take H1. I'm taking a subgroup 0 plus or minus 2 plus or minus 4 plus or minus 6 plus or minus 7, sorry, plus or minus 8, and I am taking S2 to be equal to 0, 0. So we will write in different way. So we will take 0, 2, 4, 6, 8, minus 2, minus 4 up to n. That is, I am taking H1 to be 2z and I am taking S to be equal to 3z. Nz will always be a subgroup. Remember, if z is an integer, then nz will always be a subgroup. So 3z will be 0, 3, 6, 9, 12 multiples of 3. This is minus 3, minus 6, minus 9 and so on. Now these two are subgroups. You can easily verify that one step test, that is AB inverse belongs to H. Let G be the additive group of integers. Remember, it is additive group of integers. G is equal to Z plus, right? So if I am adding 2Z means 2 plus Z, 2Z means 2Z here, 2Z means 2 plus Z, 3Z means 3 plus Z. This will always be a subgroup. So next we will be seeing cosets. So this will be very useful, right? Cosets. So 3 plus Z means I am adding 3 to all the integers. So that means 0 integers, right? So we will get 3, 0, 3, 6, 9 multiples of 3, multiples of 3. Okay. Now these are the two subgroups I have taken. Now this is a subgroup, right? So it is closed. You just take 3 plus 6, the sum is 9, it will be in G, and again we can also verify AB inverse is in H. So these two are subgroups. Now what about H1 union H2? What about H1 union H2? So if a union, what I will have? If a union is what I will have. So 0 we will have, 2 we will have, 3, 4, 6, 0, 2, 3, 4, 6, 9, 8, 12 and so on. And here we will have minus 2, minus 2, minus 3, minus 4 and next term will be minus 6 and so on. So this is the union of H1 union H2. Now is it a subgroup? It is not a subgroup. Why? H1 union H2 is not a subgroup. Why? Because it is not closed. Why? You just take A to be equal to 2, B to be equal to 3. Now what is A star B? The operation is addition, A plus B. So 2 plus 3 which is equal to 5 does not belongs to H1 union H2. H1 union H2, right? If it is closed, then sum of the elements should be in G. I am telling sum because the operation is addition. So therefore this is not closed. So therefore H1 union H2 is not a subgroup. So therefore what we can conclude is union of two subgroups need not be subgroup. So next you will ask, when will be a subgroup? When the union will be subgroups? So union will be subgroup if and only if H1 is contained in S2. H1 is contained in S2. But here you can see this is not contained in this, right? Contained means one has to be a subset of some other. 1 has to be a subset of some other. For example, if I take S2 to be equal to 4Z, if I take S2 to be 4Z, then it will be a subgroup. Why? Because 2Z and 4Z are, one is contained in other. So 2Z is 0, 2, 4, 6, 8. What is 4Z? It is 0, 4, 6, 8 and minus 4, minus 8. This will be a subgroup. This will be a subgroup because one is contained in other. One is contained in other. So union will be a subgroup. That is what they are saying, that note, the union of two subgroup is not necessarily a subgroup. If we take a subgroup S3 to be minus 8, minus 4, 0, 4, 8, then H1 union S2, S3 is a subgroup. So we shall prove that one of the following example, that union of two subgroup is a subgroup if and only if one is contained in other. One is contained in other. But if you look at this example, this is not contained in this, or this is not contained in this. Suppose if that happens, then that two subgroups union will be a subgroup. But intersection, arbitrary intersection is subgroup. Now what can I say about intersection of this? Intersection contains only 0, right? So therefore set has only 0 element, it is a group, right? If set has only one element, it is ID element, it is a group. So therefore H1 intersection S2 is nothing but 0 is the only common. So H1 intersection S2 contains only 0, so it will be a subgroup, but it is not a subgroup, right? But it is not a subgroup. Okay. So intersection of two subgroups is always subgroup. Intersection of finite number of subgroup is also a subgroup, but union need not be subgroup, and union will be a subgroup if one is contained in other. Now solve the example. Solved example. So as I already said that when doing the examples also, so example 1, let G be the arithmetic group. Solved example, exercise 1, let G be the arithmetic group of integers, then prove that the set of all multiples of integers by a fixed integer m is a subgroup of G. That is what I have said, right? So NZ will always be a subgroup. So NZ means fixed multiple, 2Z means 0, 2, 4, 6, 8, minus 2, minus 4, minus 6, 3Z means 0 plus or minus 3 plus or minus 6 plus or minus 9 and so on. So in general, NZ will always be a subgroup. NZ will always be a subgroup. This is what exercise 1. So I need to prove this. I'll take only 20, maximum 15-20 minutes. I need to finish this today. So first solved example. So what they are saying is, let G be, just go through the notes, page number 146. So let G be additive group of integers. Then prove that the set of all multiples of integers, of integer by fixed integer m is a subgroup, right? That is, if G is equal to z comma plus, then mz is always a subgroup. Mz is a subgroup. In the previous example, we have taken 2z, 3z, right? Multiples of 3. So it is not plus, right? It is m into z. Sorry, in the previous example, I have said m plus z. It is m into z. So mz is a subgroup, right? Yes. So what is G? G is 0, 1, 2, 3, 4 integers, right? minus 1, minus 2, etc. Now what about m into g? What about m into g? That is h, right? So what is h? H is m into z. So this is 0, m, 2m, 3m, 4m, and again minus m, minus 2m, and so on. Now we need to prove that this set is group, right? This set is group. Now what I am going to prove is we need to show if A belongs to H, B belongs to H, AB inverse belongs to H. If I show this is a subgroup, but here the operation is addition. So what we need to prove is A minus B belongs to H. If A belongs to H, B belongs to H, A minus B belongs to H, right? So B inverse is minus B here because we are taking G to be Z with respect to plus. So if you take any two elements, A minus B should also be in H. This is clearly true, right? So if you take A to be equal to 2m, B to be equal to 3m, what about A minus B? It is 2m minus 3m, which is equal to minus m. This belongs to G. Sorry, this belongs to H, right? So therefore, for any two arbitrary elements, if I take A to be equal to something, B to be equal to something, then A minus B also in that set. Therefore, it is subgroup. One test, one condition test, right? So that is, if you prove this alone, then it will be a subgroup. So I am taking just two arbitrary elements A and B, and I am proving that A minus B belongs to H, right? Yes. Now if you want to prove general, now here what I am taking is I am just taking two arbitrary elements and I am showing that A minus B belongs to H. If you want to prove generally, so in book what we are doing is let A is equal to some Rm. A is equal to some Rm. Here I am choosing R to be equal to 2. So let A is equal to Rm, B is equal to Sm. Now we need to prove that A minus B. Now what about what is the inverse of B? It is minus Sm, right? Because the operation is addition. So inverse of B is minus Sm. So what about A minus B? It is Rm minus Sm. So this is R minus S into M. So this is also some integer, right? So therefore let us say it is T into M. So therefore A minus B is also some T into M, where T is equal to R minus S is some integer. So therefore A minus B is also in Tm. Therefore this belongs to H, because Tm is nothing but T is some integer. So therefore integer into M will always be in H. So therefore in general, if you want to prove it, you can prove this. Or if you want to take two arbitrary elements, you can prove this. You can either take this or this. So second is, let A be an element of a group G. In the set A power n of all integral powers of A is a subgroup of G. So what we have proved now is, if a set of all integers, that m into z will always be a subgroup. So if you want to find a subgroup of integers, m z will always be a subgroup, whatever m you can take. So this exercise 2. Let A be an element of a group G. Let A be an element of a group G. Let A be an element of a group G. Then the set H is equal to A power n, and this n belongs to positive, let us say it is natural number. Then of all integral powers of A, of all integral powers of A, then H is a subgroup. It is a subgroup, right? So you just take an element in a group G, then you form the set A power n, and that will be a subgroup. The solution. Now we can easily verify this, right? So let us take some example. So let us G is equal to 1 minus 1 I minus I. Let us take A to be equal to minus 1. Now you form the set H minus 1 power n, and this n belongs to natural number. So if n is equal to 1, we will have minus 1. If n is equal to 2, we will have plus 1. So this set contains only 2 elements. This set has -1, -1, -1, -1. So therefore this will be a subgroup. This will be a subgroup. Now again you just take a to be equal to I. Now you just form the set a power I power 1, I power n, and this n belongs to natural number. Now n belongs to I. What is I here? We need to have 0, right? So n belongs to, let us say n belongs to I. N belongs to I means 0 and positive rational, 0 and positive numbers, 0 and positive numbers, right? So this n belongs to I means 0 and positive numbers. So if n is equal to 0, we will have I power 0, which is 1. If n is equal to 2, we will have I square, which is -1. If n is equal to 3, we will have I cube, which is -I. If n is equal to 4, we will have I power 4, which is 1. If n is equal to 1, we will have I. Sorry, if n is equal to 0, we will have 1. If n is equal to 1, we will have I. Yes. So you can see this set is a G. Every set is a subgroup of itself. Remember, every set is a subgroup of itself. So therefore here in this case H turns out to be G, no problem. Every set is a subgroup. Now in similar way, you take a single element and you just find all integral powers of that, then that set will be a subgroup. Now we are going to prove this. Now let A belongs to G. Now what is the set of all a power n, and this n belongs to I. Actually this n belongs to integers, right? So they are taking different signs here. Let us assume n belongs to integers, right? Sorry, it is not I, it is integer. Now what about this set? This is a power 0, a power 1, a power 2, a power 3, and this is a power -1, a power -2, and so on. So this is the set. Now we need to prove that this set is a subgroup. Now what you need to subgroup? You just take 2 random elements and you show that elements are in G. Let us take 2 elements. Let us take a square belongs to H, a cube belongs to H. Now we need to prove that AB inverse belongs to H. AB inverse belongs to H. Now what about AB? Let us take this a power 3. Now what about AB inverse? This a square into a power 3. A square into a power 3. So this is nothing but a power 5. This belongs to H, right? Because the n is n is integers. So therefore this is in H. So we have AB inverse, right? So this is -3, a power -3, b inverse. Let us take a square and let us take a cube and b inverse. AB inverse is a square, b is a cube, right? I am taking first element to be a square, second element to be a cube. So we have a square a power -3, which is a power -1, and a power -1 is in H. So therefore if you take any 2 arbitrary elements, then AB inverse is in H. So therefore it is a subgroup. Now if we want to prove more generally, what you will do is let us take so this is one way R. Let us take A to be equal to a power R, B to be equal to a power S, and this R and S are integer. Now we need to prove that AB inverse is also in H. Now what about AB inverse? This a power R into a power S whole inverse. So this is a power R into a power minus S. So this is a power R minus S, and R is integer, S is integer. R minus S is also again an integer. Let us say this is equal to T. So T is equal to R minus S. So surely this will be in H because a power T is nothing but a power integer. So a power integer is in the H. Therefore this belongs to H. Therefore this is a subgroup. Now exercise 3. So exercise 3 is, let G be the set of all ordered pairs a comma b of real numbers. So actually we have proved this. So let G be the set of all ordered pairs. Let G is equal to set of all ordered pairs of real numbers a comma b belongs to R, a not equal to 0. Actually, I already proved this, right? So the operation is if you take any two ordered pair, what you have to do is you need to find a comma b cross c comma d is equal to ac comma bc plus d. Actually, we have already proved this, right? So we need to show that g with respect to this operation is non-abelian group. This we have already proved this, so you just have to verify closure associated this. We already proved this, right? Just go through the previous first video. We have already proved this. Now, does the subset H of all those elements G which are of the form A comma B? This is a question now important. Does the subset H of all those elements thus the subset H of all those elements which are of the form 1 comma b form a subgroup of G. They are asking form a subgroup of G. Now this part you can do this, right? Because we already proved that this is a non-abelian group. Now what they are asking is the set of all 1 comma b and this b belongs to a real number is a subgroup of G. Now we need to prove whether this set is a subgroup or not. So this set contains 1 comma b belongs to a real number. This is an infinite set, right? So if b is equal to 1, we will have 1 comma 1. B is equal to 2, we will have 1 comma 2, right? Yes. Now you just go take this example which we already. So I think I lost connection. Is everything is visible? I think one is watching. You just text yes or no, visible or not. Please yes or no, quick. Yes, okay, thank you. So we need to check whether this set is a subgroup or not. So we have already proved that this is a non-abelian group. And what about the inverse? We already in that problem we have showed that AB inverse is equal to 1 by A comma minus B by A. So just go through the problem. I remember that we have did this problem, right? So the inverse of A comma B inverse is 1 by A comma minus B by A. Now we need to show whether this set is a subgroup or not. So let us take two elements in H and we will check whether AB inverse is in H or not. So if you are successful in that, then it will be a subgroup, right? So what I'm going to do is let us take two elements in H. So every element is of the form 1 comma b. So let 1 comma b belongs to H, 1 comma c belongs to H. Now what I need to prove? If I prove 1 comma b into 1 comma b into 1 comma c inverse is also in H, then it will be the problem will be over, right? Problem will be over, and here the operation is cross that we are using here, right? So this is equal to, so we will write 1 comma b as it is. Now what is 1 comma c inverse? So just substitute here. So 1 comma c inverse is, so A is 1 minus c is b, A is 1. This is 1 by 1 comma minus c, that is 1 comma minus c is the inverse, right? So you can see, so you just compare with this formula. So we have A is equal to 1, B is equal to C. So A is equal to 1, this will be 1 1, B is equal to C. So therefore we have 1 comma minus C. So inverse of 1 comma C is minus C. Now we need to make this multiplication. Remember, the multiplication what we are doing is we have to use this operation, right? If the operation is addition, you just have to add, but here the operation is this. So AB cross CD. So here the operation is cross. This is cross, right? Cross. So A into C, so 1 into 1, B into C, so B into C, so comma B into 1 plus D, so D is minus c, d is minus d. So this is equal to 1 comma b minus c. Now what is b? B is some real number, c is some real number, right? Here b and c are some real number. So what about b minus c? It will also be some real number. Let us say that number is p. Let this is p is equal to b minus c, and this p is a real number. So surely 1 comma p will also be in h, right? So 1 comma p is also in h. So therefore p is a real number. So 1 comma p belongs to h. So therefore this is a subgroup. Therefore it is a subgroup, right? So it's a very important problem. So this question can be asked in long answer. So first you have to show that this is a group by checking that closure associative ID inverse, which we already did in the very first video or second video, and in that we have said that the inverse of AB is 1 by A comma minus B by A. Now we are asking that we are taking a subset H of this form, and they are asking us to verify whether it is a group, subgroup or not. So they are taking two elements, and with the help of the inverse formula that we find here, I am using that here, and I am making an operation that is mentioned here, and I am showing that it is also of the form 1 comma p, and this p belongs to a real number. So therefore it is a group. Now exercise 4. So exercise 4 I will do, 6 I will do, fifth exercise you have to do as exercise, fifth problem you have to do as exercise. So the fourth problem is, so just for just 10 minutes I will quickly finish. So the fourth problem is, let H be a subgroup of G. Let H be a subgroup of G. Define T is equal to set of all x in G such that H is equal to Hx, Xh is equal to Hx. Show that T is a subgroup. Prove that T is a subgroup. So what we are doing is, so this is our G, this is our H. Now you collect all x in G. You collect all x in G such that x into H is same as H into x, right? You collect all x in G such that xh into same as h into x. Then this set T will be a subgroup. Then this set T will be a subgroup. So this is the one we will prove, right? So let us take two elements. So let x1 comma x2 belongs to T. What we need to prove? x1 x2 inverse is also in T. This is the one we need to prove. So we have x1 belongs to T. So if x1 belongs to T means x1 will be of the form x1h is equal to x into x1. x2 belongs to T. That means x2 will be of the form x2h is equal to hx2, right? Now we need to prove that x1 x2 inverse belongs to T, right? Yes. Now before that we will prove that x2 inverse exists, right? Yeah, we will prove x2 inverse exists. So claim, we prove that x2 inverse belongs to T, right? x2 inverse belongs to T. Then only we can find x1 x2 inverse. So first we will verify x2 inverse belongs to T, and then we will show that x1 into x2 inverse is in T, right? Yes. Now we have x2h is equal to h into x2. We have x2h is equal to h into x2. Now what I am going to do is, I am going to pre and post multiply by x2 inverse. So pre and post multiply by x2 inverse. So x2 inverse, x2h is already there, x2 inverse, this is equal to x2 inverse, hx2 is already there, x2 inverse, right? So this is pre and post multiply pre and post multiply by x2 inverse on both sides. So x2 inverse, x2 inverse, x2 inverse, x2 inverse, right? Now x2 x inverse, x2 x inverse, I can write this as I. So therefore this is nothing but h x2 inverse, and this x2 x2 inverse I can write this as I. So this is nothing but x2 inverse h. Now if xh is equal to hx means this h belongs to G, right? So that means x belongs to T. Now can I say x2 x inverse is equal to x2 inverse h? Can I say x2 inverse belongs to T? Can I say x2 inverse belongs to T? Right? So if xh is equal to hx, then this x will be in G and that will be in T. Now instead of x we will have x2 inverse. So can I say x2 inverse is in T? Yes. So therefore x2 inverse belongs to T. So this is the first line. Now we will prove that x1 into x2 inverse is equal to E. Right? x1 into x2 inverse is equal to E. We shall show that x1 into x2 inverse belongs to T. Now for that what I am going to do is, I am going to show, what I am going to prove is x1 x2 inverse into h is same as h into x1 x2 inverse. So if I prove that, then I can say x1 x2 inverse will be in T, right? So if instead of x we will have x2 x2, I say x2 inverse belongs to T. Now instead of this I am going to have x1 x2 inverse, x2 x2 inverse. So if I say this, then this will happen. So in order to prove this, I am going to prove this. So if I prove this, I can conclude that x1 x2 inverse will be in T. x1 x2 inverse will be in T. So we will prove this, right? So we will take this LHS. So x1 x2 inverse into h. Now we will arrive the RHS. So x1 x2 inverse into h. Now this I can write this as x1, and we already know x2 inverse h I can write this as h into x2 inverse. This is by, let us take this as 1, this is by 1, right? So x2 inverse h is already in T, so I can write this as h x2 inverse, h x2 inverse. I am taking this, right? So this is x1 h x2 inverse. So this I can write this as x1 into h into x2 inverse, x1 into h into x2 inverse. Now h, this is same as hx1, right? Because by this is same as hx1 into x2 inverse. So this is equal to hx1 x2 inverse. This is the one we need to prove. So therefore we have started with this and we have proved with this. So this implies x1 x2 inverse is in T. Therefore it is a subgroup. It's very easy. You just have to take a proper notes. So you just copy from here to here and then you copy here, and I am just interchanging with these three. So with these two and with this, so I am just making three conditions there to prove it is a subgroup. Now fifth problem take this exercise. It is not very important, but you just practice in your own. I will do sixth problem. Now we are going to prove the result I have said, right? Show that union of two subgroup is a subgroup if and only if one is contained in other. One is contained in other. So union will be show that union of two subgroup is a subgroup if and only if one is contained in other, right? So we will prove this. So this is the last we are going to prove, and then exercise 7 and 8 are just examples, right? So before that I will just recall what they are saying. Exercise 8, can an abelian group have a non-abelian subgroup? They are asking, right? So in exercise 8 it is nothing but true or false. So can an abelian group can have a non-abelian subgroup? It's not possible, right? So if group is abelian, then every subgroup is abelian. So therefore it is not possible, right? So therefore this will not happen. Can a non-abelian group have an abelian subgroup? It is possible, right? So it is possible for us to have a non-abelian group to have an abelian subgroup. For that we will take S4 symmetry group S4. It is a non-abelian group of order 24. So right, S4 non-abelian group of order 24. Now we just take a subgroup K4. So I think you just take a subgroup K4, right? So you just take K. Yes, they have given example, right? So a non-abelian group can have an abelian subgroup. So for example, the symmetry group S3. S3 is non-abelian, but what about A3? A3 is an abelian group. A3 is abelian group. So that of all even combination of three symbols is an abelian group. So therefore, if group is abelian, then subgroup will always have to be abelian. But if the group is non-abelian, then we can have a subgroup which is abelian. I'll repeat, abelian group, then every subgroup has to be abelian. But if the group is not abelian, there can be a subgroup which is abelian. Example is S3, symmetry group is not abelian, but I can have a subgroup A3 which is abelian. Can a non-abelian group have a non-abelian subgroup? Yes, right. So again you take S3, it is a non-abelian group. So you just take some other subgroups. So let us take I, 1, 1, 2, 3, 1, 3, 2, 1 something. That will be a subgroup, right? So all they are given examples, right? So it is already an example. Yes. Again they have taken P4 and A4 is non-abelian, right? A3 is abelian, but A4 is not abelian. Now we will prove this and then we will wind off. You just go through the one that I have said, right? So page number 149, they have asked 3 questions. So I am given answer for 3 questions. Can a non-abelian group have a non-abelian subgroup? Is it possible? So you just take a non-abelian group to be S4 and A4 is non-abelian again. So I will prove this theorem and then I will wind off subgroup. So the question is, show that union of two subgroup is a subgroup if and only if one is contained in other. So I will quickly prove this and then I will wind off. So last theorem in subgroups. They are not proved. I have only said that I am going to prove that. So union of two subgroup is a subgroup if and only if one is contained in other. One is contained in other. So if and only if, right? So you will assume that union of two subgroup is a subgroup if and only if one is contained in other. So suppose H1, H2 are two subgroups of a group G. I am assuming that it is contained. So assume H1 is contained in S2 and S2 is contained in H1. What I need to prove? H1 union S2 is a subgroup. This is the first case. I am assuming that it is contained, one is contained in other. I am going to prove that it is a subgroup, right? Yes. Now since H1 is contained in S2 and H2 is contained in H1 is contained in H1. Now H1, what about H1 union S2? It can be S2 or it can be H1. It can be H1. So since both H1 and S2 are subgroup, right? So let H1 and S2 be two subgroups. So this has to be equal to S2 or H1. In both the cases, it will be a subgroup because S2 is already a subgroup, H1 is already a subgroup. So therefore, H1 union S2 is a subgroup. It's a subgroup because because H1 and H2 are subgroups. Right, so this is the first part. Now second part is I'm going to assume this is a subgroup, and I'm going to prove that H1 is contained in H2 and H2 is contained in H. This is the second part, right? So conversely, suppose H1 is equal to H1 union H2 is subgroup. We need to prove that H1 is contained in H2 or H2 is contained in H1. So suppose assume a contradiction. Suppose H1 is not contained in H2. Let us assume contradiction that H1 is not contained in H2 and H2 is not contained in H1. So I am assuming contradiction that H1 is not contained in H2 and H2 is not contained in H1. Now this implies H1 is not a subset of H2. H1 is not a subset of H2, right? Not a subset of H2. So there exists an element A in H1 such that there exists some A in H1 such that this A does not belongs to H2. Again, very basic idea. So if this is not contained in this, means H1 is not a subset of H2. So I can find an element A in H1 that is not in H2. So therefore, there exists some element A in H1 such that A not equal to H2. Now again, so with this we will have this. So again we have assumed that H2 is not a subset of H1. So this implies H2 is not a subset of H1. So therefore there exists an element B belongs to H2 such that this B does not belongs to H1. Right? Again B does not belongs to H1. Let us see this is equal to 2. So from 1 and 2 we have A belongs to H1, A belongs to H2. Now what can I say about A? From 1 and 2 can I say A belongs to H1 union H2, B belongs to H1 union H2, right? It will be in intersection, it will be not there, but surely A and B both belongs to H1 union H2. In intersection it will be not there. In intersection both will be not there. A and B will be not there, but in union both A and B are in H1 union H2, right? So since H1 union H2 subgroup, therefore let us say therefore AB is equal to C. Since H1 union H2 is a subgroup, therefore it is closed. Now if I take two elements in H1 union H2, AB should also be in H1 union H2. So let AB is equal to C. Let us take AB is equal to C. Say C. Now we need to prove that this C is in H1 union H2. Suppose if this C is not in H1 union H2, then we can surely say that this set is not closed, right? So we should say that the product of this will be in H1 union H2. So since H1 union H2, AB is equal to C. It will be equal because we already assumed that it is a subgroup. So therefore the product of AB will also be in H1 union H2. So I am assuming that product to be equal to C. So therefore H1 union H2 is equal to C. This also belongs to H1 union H2. It will be in this because H1 union H2 is a subgroup, right? Yes. So we have AB is equal to C and this belongs to H1 union H2. AB is equal to C and this belongs to H1 union H2. Can I say AB is equal to C? It belongs to H1 union H2. So this C belongs to H1 or this C belongs to H2. It can only be in one set because it is a union. So either this element has to be in H1 or this element has to be in H2. This element has to be in H2. Right? Now if AB suppose suppose AB is equal to C belongs to H1. Now either this element has to be in H1 or this element has to be in H2. Suppose if this element AB belongs to C belongs to H1, suppose if this happens, then what about B? B is A inverse C. So pre-multiply by A inverse. So A inverse into A is I. So we have B only here. So we have B is equal to A inverse C. So this belongs to H1. This belongs to H1. Right? This belongs to H1. Now again, suppose, so therefore this element belongs to H1. Why? Because C is in H1. A belongs to H. So therefore A inverse is also in H1. So this implies B belongs to H1. But this is a contradiction, right? Because you can see this B does not belongs to H1. So by 2 B does not belongs to H1, which is a contradiction. So therefore AB is equal to C does not belongs to H1. So therefore C does not belongs to H1. Now suppose if this is equal to H2. Suppose if it is equal to H2. Now what can I say about B? It is A inverse C belongs to H2. What about A inverse C? This implies B belongs to H2. So this is again a contradiction. So by 1 B does not belongs to H2. So therefore both are not possible. Both are not possible. So B does not belongs to H2. B does not belongs to H2. Okay, we will write this as A. What about A? A is equal to CB inverse. So post multiply by B inverse. So this belongs to S2, but A does not belongs to S2. This implies A belongs to S2, but by 1 A does not belongs to S2. So again a contradiction. So therefore this element, this C, not in H1, not in H2. That is, it is not closed, right? Therefore it is a contradiction. So we are getting a contradiction. So therefore either this has to be happen or this has to be this, right? So we are asking, so what we are telling is the element C not in H1 and not in H2. That means this is not true. So we are assuming contradiction. So therefore the subgroup is over. So the next class we will start cosets and Lagrange's theorem. I will send us video. The next class we will start cyclic groups, right? So thank you, goodbye.